all these terms on the left-hand side here are scrambled. Now, one of the things I learned, at least I think I learned, is that if you take a look at the degrees, and the degrees of both sides happen to be the same, you can sometimes use what they call the arithmetic mean, geometric mean inequality. For example, this is the right-hand side has a degree, it's a single term with a degree abbreviated equals to 8, right? Now you got all kinds of terms flying around over here, but if you take a look at this term, the b c to the fourth d term, and then the AD, if you multiply these two together, this term and this term, you do get degree 8. Now, again, I'm not an authority on this by any stretch, but I think that if you have that going on where the degrees of the expressions are the same or sort of the same, then you can use what they call the arithmetic mean, geometric mean inequality. And that's what I did here. Y'all, again, this statement right here, this is what they call, both of these are AM-GM statements. That stands for arithmetic mean, geometric mean. So let me write this hyphenated here, AM, not antimeridiem, but it stands for arithmetic mean. And then this is GM for geometric mean. Now, one of the inequalities deals with addition and the other deals with multiplication. That's what makes it so fundamental. Okay, this left-hand side is certainly the arithmetic mean of these four terms, right? 1, 2, 3, 4 terms divided by 4, right? That's called the good old-fashioned mean, average, or arithmetic mean. Now, notice the similarity to the right-hand side where now the operation becomes multiplication. We have addition here, addition here, addition here. Now we have multiplication, multiplication, multiplication. And instead of dividing by 4, we're extracting the fourth root. Okay, and that's where I guess the multiplication aspect comes into play. But it's very fundamental because it links the operations of addition and multiplication in an inequality sense. So that happened twice here. We applied the AM-GM inequality twice. And then the rest of it's fairly straightforward. You can multiply inequalities, you can subtract them, you can add them. And so that's what happened right here. You can check it out and see it, but I'm pretty sure I got it all right. Right here, you see that 4 times 4 is 16, of course. And then properties of radicals means that you can just multiply it's the radical. The product of the radicals is the radical of the product, I guess, is the way to wrap that around in linguistic terms. But you go like this, fourth power, nothing's, no problem here, 4 times 4 is 16. Fourth root, and then notice that all of these exponents add up to 8. Okay, so you get a to the 8th, b to the 8th. Nice when it's alphabetical. All right, a to the 8th, b to the 8th, c to the 8th, and of course d to the 8th. So all these problems are rigged to work out. You know, they're just problems that are worked backwards. But notice this is exactly the inequality we're set out to prove right here. This is certainly equal to 16. Properties of exponents. Think of the fourth root is a to the 1/4. Multiplying exponents, you get a squared. Or you can just plain think of what's going on. You don't have to adhere to any, kind of mechanical rules. B to the 2nd. C to the 2nd. D to the 2nd. And that completes the proof, so we can write QED, thus we have demonstrated. Thanks for viewing.